So in this video I want to go over chapter 11 a little bit. Now in the lecture videos that you saw in Moodle, there's plenty of talk about intermolecular forces there. Let me do a sort of a review of this topic and how it relates to specifically physical properties, which is what this figure is trying to get across. So one thing to note about intermolecular forces, so these are, you can talk about attractive and repulsive forces between molecules. Typically we're talking about attractive forces, and that's what we're discussing here. So attractive forces between molecules. And what happens is that as the intermolecular forces increase, then the molecule essentially gets more sticky, and so they have a tendency to cling together more. And the way we see that manifests itself in the physical state is that the higher intermolecular forces will more likely to be a solid. And then on the end where you have gases, and these would be low intermolecular forces. So that's your basic trend that you see for the relationship between, again, phase and the intermolecular forces. Now the reason why this one is kind of interesting is because these are three diatomics, and as it turns out, all of the diatomics are nonpolar. Now from this trend here, since iodine is a solid, then the conclusion that we can draw from this is that this one has, and I've already sort of already mentioned it, has higher intermolecular forces. Well, we're dealing with all three halogens, or I should say all three elements are halogens. So they're in the same family periodic table. They're all nonpolar. The feature that causes this one to have a higher intermolecular force is because it has a larger molar mass. And that's just the trend that we see. Okay, the larger the molecule is, the higher intermolecular force is going to be, and the more likely it's going to be a solid. Now another way to talk about the phase that you're looking at, or another way to talk about the trends in these phase changes, if you will, is by specifically referencing like boiling point and melting point. And so, and I keep going to iodine here. Since it has higher molecular forces, yes, it's more likely to be a solid. Well, what does that mean? It means that it has a higher melting point. And not just higher melting point, but also has a higher boiling point. That's another association that we always have with these molecules with a higher intermolecular forces. Let's do a quick review of the three different types of intermolecular forces, and kind of in no particular order in a way. The first one is going to be dispersion forces. And again, if you don't mind, let me just DF for dispersion forces. And the reason why I scribbled in here is because, well, that's what you see. If you have something that's nonpolar, really the only intermolecular forces present are dispersion forces. So let's clean up the notes a little bit. So the first one to know about. So for nonpolar molecules, dispersion force is the only intermolecular force. Something else to note is that dispersion forces occur in all matter, in all molecules and atoms. And again, just to sort of kind of restate something, if I'm saying that these three only have dispersion force because they're nonpolar, and that the intermolecular force is higher because of molar mass, well, kind of to boil that down into a more succinct kind of statement, we can say the dispersion forces are proportional to the molar mass. Right? As the molecule gets larger, its dispersion forces become larger, and as a result, it's more likely to be a solid at room temperature, and the boiling point and melting points are high. Now, along with nonpolar molecules, something we learned about, chapter 10, were polar molecules. Now, this course is not designed to teach you about every little aspect of polar versus nonpolar molecules. Really what I want to get across here is just a few key points that you look for to distinguish something that's nonpolar versus polar, and then how that works into all these intermolecular forces that we talk about. Now I'm going to make a fairly broad statement here. It doesn't always apply to every molecule, okay, and you'll learn that as you move on in your other chemistry classes. But for right now, if you have an electronegative atom in the molecule, you're going to treat it as polar. And just to, since this is going on YouTube, other people may see this. How's that? So yes, there are exceptions to that statement, but don't worry about the exceptions for this class. Really, I mean, this covers most of the bases of your typical like Gen Chem experience. Now, what electronegative atoms am I talking about? Well, specifically, and I'm just going to have a very narrow focus on this, those are the big four that we always talk about with electronegativity. Nitrogen, oxygen, fluorine, and chlorine. They're all up in the upper right-hand corner of the periodic table. And what happens, and I'm not going to go through a full description of this, you can watch the lecture videos for that, it distorts electron density in the molecule. And so it gives rise to partial positive and partial negative charges and is another form of attractive force, or develops into other types of attractive forces. Actually, let me just edit that. Now let's talk about the two different intermolecular forces that are also associated with polar molecules. So the second intermolecular force, again, and this is specifically for polar molecules, you can dipole intermolecular force. And then the third one, which is actually an easier one to describe in a way, hydrogen bonding. Now the reason why I say this one is easier to describe is because you're looking for an oxygen-hydrogen bond or a nitrogen-hydrogen bond in a molecule, or hydrogen bonding also occurs in the molecule hydrofluoric acid or hydrogen fluoride. Now the reason why I wrote these in this manner is because these bonds can show up in molecules such as H2O or let's say ammonia, but you can also change, like for example with water, you got oxygen with two bonds. Those two bonds can go to other things besides hydrogen, like for example something like what's called methanol. So this hydrocarbon group that you can tag onto the oxygen, it can be anything, okay? And what you're looking for is that thing, okay? If you see that thing, then that molecule is going to undergo hydrogen bonding with itself. And it's going to increase the degree of intermolecular forces in that molecule. Now, a molecule can also be polar, okay, and have oxygen in it, but not undergo hydrogen bonding. For example, this is called acetone. It's a common solvent. You don't need to know the name of it. I'm not going to write it down here. But acetone can undergo, so one thing to note, it is polar. Let's just sort of make some notes here. Okay, so we can say it's polar because it has an oxygen in it, but there's no hydrogen bonds because there's no OH group. Okay, there's no oxygen is bonded directly to carbon. There's no hydrogen bonded to it. Therefore, it doesn't have this. Therefore, there's no hydrogen bonding here. But the fact that it's polar, it can form what we call dipole-dipole moments, or dipole-dipole intermolecular forces. So let's just recap. Right, you're looking for one of those to say, okay, you got a polar molecule in front of you. If the nitrogen or oxygen is bonded directly to a hydrogen in whatever form on the molecule, then it's going to have hydrogen bonding along with dispersion forces. I said dispersion forces are proportional to molar mass. Well, all these molecules have molar mass. So all of these, we'll say all polar molecules also have dispersion forces. So like the water molecule can undergo dispersion forces as well as hydrogen bonding. acetone undergoes dispersion forces, it has mass, it is matter, therefore it can undergo dispersion forces. And then since it's polar, it can undergo dipole-dipole. And again, we'll rely on the lecture videos to go into much more detail than what I'm doing here. This is just a brief overview. Now, before I end this first video for chapter 12, I do want to make a little comment here. When we talk about this notion of a nonpolar molecule, yes, definitely the diatomics are, okay, so yes, that's true. But there's another group that are very commonly referred to, or very commonly used when we talk about dispersion forces, or I should say, when we talk about nonpolar molecules. And these are hydrocarbons, such as, and it could be really, any kind of string of C's and H's in some kind of formula. If you only see carbon and hydrogen in the formula, then it's a hydrocarbon, therefore it is nonpolar. Again, my goal in this class is not to cover every little nook and cranny of this topic. It's to give you kind of a working vocabulary of the different terms. And then as you take more chemistry courses, then you can sort of fine-tune your understanding of these different topics. Okay? That's enough for this first video for chapter 12.